Now for a few topics on Lebesgue integration, further topics, is the title of Chapter 5. Section 5.1, Uniform Integrability and Tightness, a general Vitali convergence theorem. So we just saw at the end of Chapter 4 in the Vitali convergence theorem that if we had a set E of finite measure, that was the restriction we're going to swap for a different hypothesis. But if we had a set of finite measure and we had a sequence of functions which was uniformly integrable, then the limit of the integrals is the integral of the limit function with a pointwise convergence of that sequence to some function f, usual type convergence theorem. So the plan here is to modify this hypothesis of finite measure. If we simply drop the hypothesis of finite measure, then we don't have a convergence theorem. We can show the finiteness as a necessary condition with the following example. Suppose f sub n is defined as a characteristic function on the closed interval from n to n plus 1 for each natural number. So when we integrate these functions, it's just basically a step function, 0 everywhere except on that interval of length 1 where it takes on the value 1. So the integrals are all 1. They're even Riemann integrable, in fact. And the limit function is the 0 function. The function, let's call it f, identically equal to 0 throughout the whole real line. And this collection of functions is uniformly integrable. If I choose a set of sufficiently small measure, the integral of f sub n over that set can be made as small as you like. That's simply because, well, when I integrate over any set, a function like this, we're going to get at most 1 out. And if we chose a subset of the interval n to n plus 1, then we'll get out, for the value of the integral, the measure of that set. So by making the measure of the set small, the values of the integrals will be small. Given the way this is defined, I'd expect those values often to be 0 even. So we do have uniform integrability for this family of functions. We do have pointwise convergence to the 0 function, but the limit of the integrals, well, all the integrals are 1, so the limit's 1. That doesn't equal 0, which is the integral of the limit function, the integral of the 0 function over the whole real line, say. So we don't have a convergence theorem. So simply dropping finite measure won't do. We'll have to add another hypothesis in. What we're going to do is replace the condition of finiteness in measure, the finiteness of the measure v, with a different condition on the sequence of functions. And that condition will be called tightness, as the title of the section suggests. First, a little result that kind of motivates our definition of what it means for a sequence to be tight, or a family of functions is how we'll define it. Let f be integrable over set E. Then for each epsilon greater than 0, there's a set of finite measure E sub 0 for which the integral over the complement of E sub 0 with respect to the domain of the function f, absolute value of f is less than epsilon. The integral over E set minus E sub 0 of the absolute value of f is less than epsilon. So there's some finiteness imposed. That finiteness is the integrability of the function f. Let's look at a proof of that. Okay, so we're looking for set E sub 0 of finite measure such that this occurs. So let epsilon be greater than 0. We've hypothesized that f is integrable. That's equivalent by the very definition of integrable to saying that the absolute value of f is integrable over E as well. So we'll just consider the absolute value of f. Now, absolute value of f, that's a non-negative function. The way we defined integrals of non-negative functions was in terms of suprema of integrals over bounded functions of finite support. They were effectively class 1 functions, is how I had worded it in the past. We might be integrating over a function of infinite measure, but the integrating over a set of infinite measure, but the function itself is only non-zero on a set of finite measures. So we're effectively bounded functions on sets of finite measure, the verbiage we used in the past. But we had defined the integral over e of the absolute value of f in that setting then of a non-negative function as a supremum of the integral over e of g of all g that were non-negative and less than or equal to the function we're integrating, the integrand, absolute value of f in this case, where g was a bounded measurable function which vanishes outside a set e sub 0 of finite measure. That's the finite support part. So the finite support part gives us this set e sub 0 of finite measure when we look at a particular function g. We want a function g such that the integral over e of the absolute value of f minus the integral over e of g is less than epsilon. Remember, we define these symbols, the integral over e of the non-negative function absolute value of f, we define that integral to be a supremum over all such g. Well, if this is a sup, then for one thing, the integral over e of g, all these are less than or equal to the integral of over e of the absolute value of f. All of these are less than or equal to the sup of the set of those. So we're dealing with something non-negative here. Also, what we're saying is, if you'll back off a little bit from the sup of the set, then we start finding elements of the set. A property of suprema allows us to extract this, and we've used this argument before. So there exists the set e sub 0 and the function g such that we get this kind of behavior. The e sub 0 is the set of x values outside of which function g vanishes. Function g is 0. Okay. So we want to show the integral over e set minus e sub 0, absolute value of f, is less than epsilon. So here's the argument. We'll integrate over e set minus e sub 0, absolute value of f. That's the same as integrating the absolute value of f minus g. G vanishes outside of e sub 0. That is, g is 0 outside of e sub 0. And we're only considering points outside of e sub 0 when we integrate over this set. So I can subtract the g, that changes nothing on the set e set minus e sub 0. We are now going to take this quantity and add to it the integral over e sub 0 itself, absolute value of f minus g. So we've added this number. This is a non-negative number because absolute value of f minus g is a non-negative function, follows from the inequality right there. And we're integrating over some set e sub 0. So we integrate a non-negative function over a measurable set, we get a non-negative integral. That's all. So we've pick up a less than or equal to at this stage. Now we're integrating, notice the integrands are the same, over e set minus e sub 0 here, and over e sub 0 itself here. Additivity from the appropriate setting, Theorem 411, that must be non-negative functions. So additivity is applied to non-negative functions, imply that this equals the integral over e of the integrand, absolute value of f minus g, less than epsilon. Absolute value of f minus g, which we can show is less than epsilon, I should say, by what we have up here. Maybe another step could be inserted using linearity and what we've got here. So linearity is applied to this integrand, producing the difference of the integrals, and that we know to be less than epsilon, and that's where the less than epsilon comes from. So integral absolute value of f, e set minus e sub 0, less than epsilon. The e sub 0 came rather indirectly from the epsilon and the definition of the integral of the absolute value of f. All right, this idea, when applied to a whole family of functions in a uniform way, the expression we're going to use is that a family of functions is tight over a set E if it satisfies this type of thing described previously. It's a uniform kind of thing, though, as you can see, because we're requiring that for all functions in the family, certain conditions hold. So there's a uniformness of this tightness idea. And the formal definition is a family, calligraphy F, of measurable functions is said to be tight over set E, provided for every epsilon greater than 0, there's a subset, E sub 0, subset of set E, of finite measure. All right, so we're throwing out a set of finite measure effectively, for which the integral over E set minus E sub 0 absolute value of F is less than epsilon for all functions in that family, in that set. So I argue, I'd call this uniformly tight or something like that if I were me, which I am, because of this for all idea. So there's something related to uniformness in this. And what we're going to do in the generalization of the Vitali convergence theorem is replace the finite measure requirement on set E with a tightness requirement on the sequence of functions. And that'll give us a generalized convergence theorem, the general Vitali convergence theorem. Quick little observation. If we take F to be from a family where that family is uniformly integrable and tight over E, so both uniformly integrable, the integral over a set A of the absolute value of these functions can be made small. And tight is just defined throwing out a set, E sub 0, we get a behavior like this. If we have both of these holding, then there's a finite measure set, E sub 0, such that the integral over E set minus E sub 0, the absolute value of F is less than epsilon. That's the tightness property. Proposition 4.23 says, if you have uniformly integrable and a set of finite measure, then such a function must be integrable over that set of finite measure. Let's take a quick look at theorem 4.23. It's the conversely part here. It says if we deal with a set of finite measure, it's a set E sub 0 in what we're having, in the conversation we're having right now in section 5.1. So it's E sub 0, that's the set of finite measure. And if for each epsilon greater than 0, there's a delta greater than 0 such that we get this type of behavior here. This we called uniform integrability, mimicking what we're doing now. We stated a proposition and then we followed it up with a definition. So this other stuff is saying if we have a set of finite measure on which we have uniform integrability, then such functions must be integrable over that set. So it's a conclusion of integrable over sets of finite measure, back to section 5.1. And that's what we're looking at here. We got a set E sub 0 of finite measure. We've got uniform integrability over this family along with some other stuff. So F must be integrable. So any F in this family must be integrable over E sub 0, the set you threw away. It's also integrable over E set minus E sub 0, the remainder of, if you will, the domain of the function. Its integral's even small there. But we've got finiteness if we integrate over E sub 0. We've got an integrable function over E sub 0. And we've got a small integral up here, finiteness there as well. So we can draw the conclusion that function F and its absolute value are integrable over all of set E. Punchline here is uniformly integrable and tight over a set implies integrable over that set. The general Vitali convergence theorem says, let F sub n be a sequence of functions on E that is uniformly integrable and tight. No hypothesis of finite measure of set E like there was in the regular Vitali convergence theorem. Suppose F sub n approaches F pointwise almost everywhere. So convergence theorem, we need a sequence of functions in pointwise convergence, almost everywhere pointwise convergence. The claim is then F itself is integrable over E, and the limit of the integrals is the integral of the limit. So our last convergence theorem, typical convergence theorem conclusions. Two claims, F itself is integrable. We just put together a claim in this previous observation, note 5.1.a. I'll refer to this in the proof. This applies actually to the F sub n's. They're the things that are uniformly integrable. Right, so the note here will apply to the f sub n's to draw the conclusion that the f sub n's are integrable over E, not f itself. Right, that's the limit, and this doesn't deal with limits. It deals with elements of the family, which is uniformly integrable and tight. So in this case, note 5.1.8 deals with the f sub n's, not their limit, not the f function. All right, so for proof, this is an epsilon halves, actually maybe a couple epsilon halves arguments. First, an epsilon fourth argument with two of these to get the first epsilon halves, and then a second one for the rest of it. But epsilon be greater than 0. We're trying to show f is integrable, and we're trying to show the limit as n approaches infinity. The integral of the f sub n's equals the integral of the limit function f. Okay, so we'll consider a difference of these things here, and that's where the epsilon will come into play. Let epsilon be greater than 0. Since f sub n is tight over set E, there's a measurable, E sub 0, a subset of E, a finite measure. E sub 0 is a finite measure, for which the integral over E set minus E sub 0, the absolute value of f sub n, can be made small. I choose small to be epsilon over 4, so this will be about a quarter of the inequality we'll ultimately need. And this holds throughout the family of functions. That is, it holds for all values of the index, as we've assumed this sequence is uniformly, the sequence is tight. So there's the use of the tight condition. Fatu's lemma will apply to say, okay, let's take a limit. Fatu's lemma says the integral of the limit is less than or equal to the lim-inf of the integrals, right? It was an inequality in a lim-inf. Setting here for Fatu was non-negative functions, and we've got absolute values on everything. So we've got non-negative functions, so Fatu does apply. To draw the conclusion that you get the sequence, it converges pointwise almost everywhere to function f, then the integral of the limit function is less than or equal to the lim-inf of the integrals. Now, these integrals for all n are bounded above by epsilon over 4. So when we take a lim-inf, that lim-inf is also bounded above by epsilon over 4. In the limit process, we pick up an or equals to there. But there's your integrability of f over this set. So integral E set minus E sub 0, absolute value of f, is bounded. It's bounded by something small even. So we've got f is integrable over E set minus E sub 0. We've claimed that f is integrable over E, so that's only part of it. So we're not done with that piece. Also, if we'll integrate E set minus E sub 0, f sub n minus f, let's take an absolute value of that, pass the absolute value inside the integral comparison test, proposition 416, allowed us to do that, picking up an inequality in the process as given. All right, let's continue from there. So here's that last equation written out without the explanation. Pointwise, let's apply the triangle inequality. So f sub n of x plus the absolute value of f sub n of x plus the absolute value of f would be greater than or equal to what we have here. Apply the triangle inequality to break this up pointwise, and then apply monotonicity in the appropriate setting. The absolute values tell you this setting is non-negative functions. So triangle inequality followed by monotonicity of the integral will produce this inequality and this integral here. On the previous slide, we showed these were each less than epsilon over 4, and we showed that this was less than or equal to epsilon over 4. So pasting those two together, we must be halfway there. There's the epsilon halves part. What we're lacking here is we're still integrating over E set minus E sub 0, and we need to be looking at the whole set E. Well, this is part of it, half of it probably, in a sense. All right, E sub 0, that was finite measure. We threw out a set, E sub 0 of finite measure, blah, blah, blah. And we had integrals that were small. That's what the tight property was. So the E sub 0 set has finite measure. So what happens on the E sub 0 set? Well, f sub n is uniformly integrable over E sub 0. if it's uniformly integrable over E, it's uniformly integrable over a subset of E. Each f sub n is integrable then over E sub 0. That's, if you like, that's that note 5.1.a was mentioned. Proposition 4.23 was mentioned in the note. So we've got uniformly integrable, a collection of functions which are integrable, why the Vitali convergence theorem applies in that setting. If we had a sequence of integrable functions where the sequence was uniformly integrable and the set had finite measure, Vitali convergence theorem applied. So the Vitali convergence theorem applies, but only on the E sub 0 part. So we draw a conclusion from the Vitali convergence theorem that f is integrable over E sub 0, and the limit as n approaches infinity of the integral over E sub 0 of f sub n equals the integral over E sub 0 of the limit. So Vitali convergence theorem gives us this limit equation and the integrability of f, but all this stuff is happening over E sub 0. And we need to paste that together with the information we already have concerning E set minus E sub 0. But I'm not surprised in a generalized version of the Vitali convergence theorem to see the regular old Vitali convergence theorem rear its head. All right, so let's take this limit definition here and write out some stuff in terms of epsilons. Saying the limit of this sequence of numbers equals that number is equivalent to saying there's some capital N such that when the index, lowercase n, is sufficiently large, that is greater than or equal to capital N, then we can make these things close to each other. The absolute value of the difference, if you like, linearity applies here. We're dealing with integrable functions here. So we can write the difference of the integrals as the integral of the difference, a linearity property. We can make that as small as we want. Let's make it epsilon over 2 to match up with this. So up here we dealt with the E set minus E sub 0 part. Down here we're dealing with the E sub 0 part itself. We observed f was integrable over E set minus E sub 0 on the previous slide. F is integrable over E sub 0 is observed here. Additivity will give you integrable over set E. So it's integrable over two pieces of set E. It's integrable over set E. And each f sub n is integrable over set E as well. I can get that if you like from note 5.1.a or similar observation. We've dealt with E set minus E sub 0 and we dealt with E sub 0 itself here. But everything's integrable is the conclusion on that part. We're trying to show this kind of limit thing. We're trying to show a convergence theorem, but over set E, not set E sub 0. So that's what's left to be done. All right, so we'll take the integral over E of f sub n minus the integral over E of f, absolute value of. We want to make that small, we'll make that less than epsilon. Linearity will allow us to write that that difference of integrals is an integral of a difference. We're dealing here again with integrable functions. Everything inside is integrable. So it's the section concerning integrable functions. The general Lebesgue measure, I think, was a section that contained these results. So linearity allows us to get this. We're going to split it up into pieces using additivity from that same setting and take set E and write it disjointly as E set minus E sub 0, union, disjoint union, E sub 0, and then do the additivity property. Triangle inequality, it's just two real numbers. Triangle inequality on the reals. Get an inequality here and a summation of absolute values here. This we had less than epsilon halves initially. This we just showed on the previous slide was less than epsilon over 2. Adding together, we've shown, it's back there somewhere in the previous slide, there exists a capital N such that when the index lowercase n is greater than or equal to capital N, these two things are within epsilon of each other. In other words, the limit of this sequence is that number. The limit as n approaches infinity of the integral over E of f sub n equals the integral over E of f, our last convergence theorem. So what we've done is altered hypotheses a bit to give us yet another convergence theorem. This one holding on sets that don't necessarily have finite measure. Yeah, but this concept of tight has been introduced on the sequence of functions as well. The next result is kind of similar to how we ended section 4.6. It was in Theorem 4.26. What we're considering here is a sequence of non-negative integrable functions that converges to 0 for almost all x and z. So there's the limit function right there, the pointwise limit almost everywhere. And the claim is we get the limit of the integrals to equal the integral of the limit function, integral of the 0 function, which of course is 0. This happens if and only if h sub n is uniformly integrable and tight over set E. Is the claim. This is to be shown in problem 5.1, I guess it is, in the exercises. Well, that means we're getting the limit of the integrals to be the integral of the limits in some particular setting, if and only if we have uniform integrability and tight. So there's no possibility of weakening the hypotheses in the general Vitali theorem, general Vitali convergence theorem. In Theorem 4.26, we had a similar result showing that we couldn't weaken the hypothesis of the measure of set E being finite. We didn't weaken it here, we kind of changed it. We swapped that condition for another condition, the condition of tightness of the sequence of integrals over set E. And that's the general Vitali convergence theorem. Our last convergence theorem, in a sense. We're going to talk in the next section about convergence and measure of a sequence of functions. And we'll be able to recycle a lot of what we've done and kind of generalize the convergence theorems we've had. Every one of them so far has involved the sequence converging almost everywhere pointwise to some limit function. In the next section, we'll replace that idea of convergence with a different kind of idea of convergence called convergence and measure. And all our convergence theorems that we've encountered so far will carry over with that type of convergence of the sequence of functions versus regular old pointwise convergence. And what we'll have is a generalization of pointwise convergence, this convergence and measure. So I'll see you there in section 5.2, and we'll take care of a little topic there. In 5.3, another little topic related to integrability, the Lebesgue integrability, as we've defined Lebesgue integrals in the previous chapter. And that'll conclude chapter 5 and pretty much conclude real analysis 1. I'll see you in the next section shortly. Have a nice day.